Okay, so this seminar is about power electronics. During the seminar, we will talk about the circuits, components in power electronic circuits, and also we would talk about the applications of power electronics, especially in automotive. And in this seminar, we would cover four main parts. The first part would be an introduction to power electronics and the basic applications, also again the application in vehicles. And then we would spend most of the time of this seminar to talk about the circuits, includes DC-DC converters and inverters. When we talk about inverters, which is from DC to AC, we would also mention the pathwise modulation, which is the way we control the inverters. And then we would talk about the design considerations. Mainly, we would cover the active and passive components. Active components means switches that we can control them to be on and off. The passive components are capacitors, inductors. Then after we talk about the components, we would talk about the system level issues, which includes EMI and NVH. At the end, we would talk about the future development, and then we would have a very quick summary of the seminar. So, Session 1. The introduction to power electronics and its applications in vehicles. In this session, we would first answer several basic questions. What is power electronics and why we need it? Basically, what are the applications? And then we would talk about the essence of the power electronics, which is switching. And by introducing several generic circuits, we would also introduce how to analyze the circuit and the switching functions, the way that we can use mathematical tools to describe the relationship between the voltage and the current in the circuit. And then at the end, we would have an overview of power electronics in hybrid electric vehicles. So, first question, what is power electronics? Basically, power electronics is the magic of converting and controlling the electrical power from one format to another. The basic power electronic circuits, including DC-DC converters, AC to DC converters, DC to AC, and AC to AC. So here we have some examples. Let's look at our regular laptop computer. So it receives 110 AC and then it converts to 15 watt DC. And then this 15 watt DC will be fed into the computer itself. So the adapter usually would see on the left hand side corner here. This guy basically is a power electronic circuit. Usually it is isolated AC to DC converter, which means inside you have isolation, which means transformers, and it takes in AC voltage and first transfer it to DC, and then isolation, then DC to DC down to 15 watt. And then in the computer itself, we have CPU. And the CPU itself usually needs very small voltage. And when we look at this table, if we just pick a quadro-core processor from Intel, the input voltage is 1.6 watt, but it needs 150 watt. So inside the computer, that is that is a converter, a DC-DC converter. Change the voltage from 15 watt to 1.6 watt, and the peak power could be as high as 115 watt. So that is inside every laptop computer. And then DC to AC. So this picture may be familiar to all of you. This is the drivetrain of Chevy Volt. And then what we are looking at is that at the back we have a battery pack, and at the front that's power electronics and electric machine, so somewhere buried here. And then what happens is that the battery is a DC component. It generates DC voltage and current, and the power electronic circuits takes in the DC and change it to variable frequency AC to drive the machine. To make the machine, the electric motor, to run at desired speed and provide desired torque, we also need to sense the current goes into the machine, and also we need to measure the speed. So those signals are feedback, and then the feedback to a controller, and the controller would control the power electronic circuits to generate desired AC voltage to drive the machine. And then AC to AC example. The most simple one, or most common one nowadays, is wind power. So when wind blows, basically the wind speed is always changing, it's not constant. And then in the wind turbine, there's usually an electric machine rotating with the speed of the wind. So the output AC voltage of this machine usually has variable frequency, very unstable, and it is variable frequency and variable amplitude. But when we look at the utility side, basically the electricity generated by the wind power, by the wind turbine, needs to be fed into the utility side. So the utility side usually has constant AC voltage at constant frequency. So how to change the variable frequency with variable amplitude to fixed frequency and fixed amplitude? What we use is power electronic circuit. So that's the one in the middle. So when we look at the power electronics itself, actually it is an interdisciplinary technology. We have the devices and the circuits. The devices again includes active device and passive device and all kinds of circuits. And then we have when we try to use this circuit for different applications, let's say utility applications and the things we care about in this seminar, the applications of power electronics in vehicles, we will need some type of control. And also the control could be categorized into basic level of control of the circuits and high level control of the system. At the circuit level, what we usually have is pathwise modulation to control the converters and the inverters. And then based on the machine model, let's say you are driving using the power electronics to drive the electric machine, then by using the feedback signals as we showed earlier, you can use the machine model to control the machine. And then if you want to make the machine to run at a very good performance, then some advanced control series could also be applied. So in a nutshell, power electronics is an interdisciplinary technology. You need to understand circuits, device, and the control strategies, the control technologies, and combine all of this to serve different applications. So talking about applications, we have the applications in electrical power transmission at a megawatt range, and then all the renewable energy needs to be connected to the grid through power electronics devices. And a home appliance, to make our home appliance more efficient, what you do is put a variable speed drive into refrigerators, dishwashers, and the washer and dryers. So basically by doing that you would have much higher efficient home appliance, and you are paying less in your electricity bill. And then we have the industrial motor drive, medium and high voltage electric machine drives. The picture I'm showing here is an offshore drill, wire drill. Basically inside that's a high speed electric machine to drive the drill to drill the wire, to drill the into the seabed and get the wire out actually. And then we have switching power supply, which we showed earlier. Then for militaries, the power electronics are used in battleships, submarines, and tanks. They are used as power supplies or the drives for electric machines. And the locomotives, basically power electronics are used to drive the high-speed motors or high-power motors, electric machines, to make sure the locomotives can run at the speed and the power that are desired by the customers, the passengers. And finally, the focus of this seminar, automotive. So right now, the biggest applications of power electronics in automotives is different converters and inverters in hybrid electric vehicles. So what is the essence of power electronics? Basically just one word: switching. So let's say what we are showing here on this slide is the very simple comparison between a switched case and a non-switched case. Beginning, let's say we do not have power electronics and we want to adjust the current goes through a load resistor, this guy here. So we want to adjust this current. Then one way we can do it is to introduce a resistor, and this resistance is adjustable. So by changing this resistance from maximum to 0 or to a certain value, the current can goes up gradually, and finally at a proper resistance we can have a constant current. So this is very simple, but it does has a problem. The problem is that when you have a resistor to function as an adjustment unit, then what you have is additional power loss, power consumption on this resistor, which we usually say is the power loss with the power consumption that we do not want. So it is a power loss. And if these two resistors, the R and the RL, which is a load, are same, basically equal to each other, then the power loss can be 50%. And then if we do have controllable switches, things can be changed. So let's look at the case we are using power electronics devices. On the right hand, what you see is a very typical DC to DC converter structure. So what you see is that you have a DC source, and then you have a controllable switch. This switch S1 can be controlled on or off based on certain control signal. And then let's say if this switch is closed, when the switch is on, then you see on the screen you have a green dashed line. Then the current would go through this green line, and then it means the power supply is connected with the load resistor. And then you can control this switch to be off. Now when the switch is off, this loop on the left hand side, which includes the switch and the power supply, these two are cut off from the circuit. But you do have an inductor in this circuit, so you have this guy here, and the inductor would try to push the current flow, and the only way the current can flow in this case is through the right dashed lines. And then during this time, basically the energy stored inside the inductor is dissipated into the resistor. That's the reason when you look at the waveforms here, the green bars, each of this green bar on the screen basically stands for the time length of the switch when the switch S1 is controlled to be on. And then when the green bar becomes disappears, that means the switch is off. And then when the switch is on, basically because of the power supply, you would see the current goes up. But when the switch is off, the inductor current is decreasing, because the inductor here is the only power source, so it is dissipating energy. So that's the reason you see the current is off. But by changing the on-off ratio of the switching S1, gradually you can adjust the current, the average current that goes through the inductor to be at a certain value. So this is our average current, and this average current could equals to the case of the circuit with only resistor. And then what you see is that only look at the DC component, these two circuits have the same function. But in the circuit with power electronics, you do not have additional resistors. What you have is switch S1, diode D1, and an inductor. Ideally, S1 and D1, they will not present as a power loss unit, because when they are on, that would be 0 voltage across them. That's short circuit for this guy here. So when it is on, it's a short circuit. But when it's open, it is open circuit. So either way, there will be no power loss in S1, and the same thing for D1. There's no power loss in it. An inductor, ideally, it is an energy storage device. So it does not consume real power. It stores power and then releases power to the circuit. So when you look at this circuit here, ideally the only thing that consumes real power is your load resistor. So if you do have perfect devices, and if you do not consider small resistance in the winding, then you have a 100% efficient circuit. So comparing to the traditional case, when you use a resistive device or use a linear circuits to adjust the current or voltage, one of the best benefits of power electronics is high efficiency. And also with power electronics, you can adjust the amplitude much easier, because the switches can be digitally controlled. And another name, earlier name for power electronics is digital transformer. When you think about AC, you can use transformer to change the amplitude of the voltage. And now for the DC, what you do is use power electronics to change the amplitude. So sometimes people call power electronics as digital transformer. Okay, that's the reason. And then talking about switching devices, we can have different categories. If you look at the columns here, we have uncontrollable devices. Basically, it's the diode. And then in these uncontrollable devices, the diode is only unidirectional. So it means the current can only go through one direction. And then for the controllable devices, you have two kinds of controllable devices. One is a device that you can control it to be on, but once the device is on, if you do not apply negative voltage to the anode of the device, then the current is not going to zero. Then the device would remain at on state until either the current goes to 0 or the voltage becomes negative. Then the device would be off. But before the device is on, the only thing you do have the capability to put a trigger into the device, current trigger into the device to turn the device on. But then again, once the device is on, only at these two conditions, either the current is 0 or the voltage is smaller than 0, then the device will turn itself off. So this kind of device it can be combined together to form a bidirectional device as a triad. And then for the controllable on and off, we have transistors. Transistors, basically we would operate it in the nonlinear region, basically saturation or blocking region. And the MOSFETs, then the GTOs, that's gate turn off transistors. IGBTs, that's isolated gate bipolar transistor. And nowadays in vehicles, most of the popular devices are MOSFETs and IGBTs. MOSFETs are usually used for low voltage and high current applications, and IGBT usually is high voltage and low current. That's in the traditional case. But in nowadays, actually, the voltage rating of the MOSFET is also increasing, and the same thing for IGBT, the current rating is also increasing. For example, in Toyota Camry, the electrical drive for the motor has 3-phase IGBTs in it, and in each phase the IGBTs will conduct 600 amp, and the DC voltage at the time, the voltage course switch could be as high as 650 watt. So it is felt large current and large voltage, but it is realized by IGBT. Okay, that's isolated gate bipolar transistor. So these are the single device, but if you put parallel diode, then you can make the current go both directions, either go through the controllable switch following the direction. For example, the IGBT is from the collector to the emitter, or it can go from the cathode of the diode to the anode. The anode of the diode to the cathode of the diode. And then same thing for the GTO. You can do a anti-parallel diode. And the MOSFET, most of the MOSFET, it came with a body diode. So in the structure itself, it would have a MOSFET and a diode, and it's in a single die. But for IGBT, you do need 2 separate silicon die, one for the IGBT itself, another for the parallel diode. And then let's look at some examples of the switching devices. The smallest one are the surface mount devices. So you have the diode like this, and when you compare this to a dime, it is really small. And then you have a MOSFET. This power MOSFET can be surface mount, and most of the common packages are TO220, TO247, still not very big. And then go to higher power, you have thyristors, GTOs, the gate turn off thyristors, and they actually are bundled with the heat sinks. So in the center you have the thyristor or GTO, and then you have this big size heat sink on both sides, and the heat sink could be water cooled, so you have the inlet and outlet. And then IGBTs, the picture shown here is a very large power module, and the voltage for this kind of module is usually as high as 3300 watt, and the current can be as high as 12 1200 amp. And the size of this module, actually, it is just as the size of typical lighter size paper. So think about this: you have such a high voltage, 3300 watt, and such high current, 1200 amp, but it is in a very small package. And then to these devices do have some power losses, because all the device is not ideal. When the real devices, when they are controlled on, they would have some residual voltage, and then those voltage combined with the current flows through the device would provide some power loss. And then you do need a heat sink to cool the device. So that's the reason we see a water-cooled heat sink under the IGBT modules. So basically, the way the IGBT module showed in the last slide is made from, first thing, the wafers, the silicon wafers. And in this wafer, you see that's lots of small chips. And then you take these chips out and you put it into a module. And then in this picture of inside structure of the IGBT module, the one I just circled, the bigger one, is a IGBT chip, and a small one I circled in blue, that's a diode chip. And this module is from prayers. Basically, this is the IGBTs and the diodes in the electrical drive of prayers, Toyota Prius. And then if you do put this kind of silicon dies into a module, and then you put circuit boards on top of it to control them, and then at the end you put a cover, it looks like this, which is the picture we showed in the last slide. Okay. So this slide basically shows another view of what could be inside, also the structure of the power module. Basically, from the bottom level, what you see is a heat sink. So this is a heat sink, and that does not belong to the module itself. And then on top of the heat sink, the green layer, it is a copper plate that is integrated with the power module itself. And then the most top structure, you see there are two chips in color red. Those are silicons, the IGBTs and the diodes, and they are mounted to the base plate. And for the electrical isolation, in between you have a blue layer, and this blue layer is the substrate. And this substrate basically gives you the isolation between the chip and the heatsink and also the base plate. And how to get the power out of these silicon dies? Basically, we use aluminum wire bond. So those small tiny cables are aluminum wire bond, and they are the major conductors that extracting current from the silicon die to external structures. And when you open it, it looks very fragile. Let me just go back one slide. When you look at this picture again, you see there are lots of wires on top of the chip. Basically, those are the aluminum wires, the wire bonds. Okay, so we just talked about the switching devices, and in this slide and a couple slides following this, I would give you some samples of the inverters and converters. And these are the circuits that has those power electronic switches integrated inside and together with capacitors and inductors. In this slide, one of the highlight is the Toyota Camry inverter box. And this inverter box actually this box has 3 major circuits in it. 2 inverters. So one is for the motor, another is for the generator. The motor is 105 kilowatt and the generator is 75 kilowatt. And then that's a boost converter which translates the 250 watt DC from the battery to 650 watt DC needed by the inverters, and that the power rating of this boost converter is 30 kilowatt. And the whole thing is designed to fit into a traditional place that is reserved for a 12 watt battery. So that's the reason when you open the hood of a Toyota Camry, you would not find a battery, but you would see this inverter box. And the battery itself, the 12 watt battery, the auxiliary battery, is put in the trunk of the Camry. And then for locomotive, this is an inverter I participated several years ago. It's 1.5 megawatt locomotive drive, and the size of this is like a quarter of a regular table, basically a table you would often see in an office cubic. And then the power module in this guy basically is the one we showed earlier, the 3300 watt 1200 amp module. And then this is a little bit advanced circuit. Basically it's used for medium voltage drive, and in this circuit you have multiple small converters connected in series and then in parallel, so give you very high voltage capability and also at the same time give you very high power capability. So those are the samples of inverters and converters, basically how they look like. But what are really inside actually can be explained by some very rough generic circuits. And then let's first start with a rectifier. So let's say you have an AC source in this case, and then you want to power on a load, and the load needs DC. So what you can do is to control the switch S1 and S4 at the same time, and S2 and S3 at the same time. And when you look at this circuit, basically if you have S1 and S4 at the same time, you can draw this line. Then you would see during this time the voltage across the load, basically the V2, is equals to V1. And that's the reason when you draw the waveform during this particular time period, the waveform would be exactly same of the input voltage. And then let's say the load is pure resistive, and you turn off the S1 and S4, and then a little bit time later you turn S2 and S3 on. So you have this time period, and that's S2 and S3 on. So let's see how the circuit will work. So still you have the same power source, and then when it comes to this junction point, S1 is off, so it goes down to S2, then goes to this load, and then through the load goes through S3, come back. And then in this case, if you say this is point A here, then you are connecting point A to the bottom of the load, and the point B to the top of the load. right? And then what you see here, the relationship between V1 and V2 is that V2 would equals to minus V1. And then in this particular case, when this happens, that's at the time V1 is negative. And then when you have negative, and then the V2 is the opposite of negatives because it equals to minus V1. So the waveform is flipped and it becomes positive. That's the reason during one fundamental cycle, which means this cycle here, you always has positive output with a positive voltage cause your load. So this sequence could be repeated. And then this tells us actually the relationship between the input side voltage and output side voltage can be presented by the status of the switches. So what we can say is that V2 would equals to S1 minus S3 multiplied by V1. So in this equation, S1 equals to 1 when it is on, and it equals to 0 when it is off. Same thing for S3. So if you use this kind of definition and then you put this definition into this equation here, you would see this equation is the best description of the relationship between the input voltage and the output voltage. And this equation usually is called a switching function. It tells you when you try to do the mathematical model, the instantaneous model of the power electronic circuit, you can simply use a switching function only involves 1 or 0. It's like a digital circuit to represent the circuit itself. And then another way to understand power electronics is that the power electronics is a high power, or it's a power amplifier for digital signals, but with additional passive components. So if you only have digital signal, let's say you have this digital signals, but you would not have, but after the amplifier, you see your voltage actually changes to this different waveform. That's because you do have passive components, either because the source has this kind of waveform, or in the load you would have capacitors and inductors to filter out your to make the edges of your digital signal smooth, or change the waveform a little bit. So that's a basic idea. And then let's do a little bit of exercise together. So still we have the same circuits as what we showed in the last slide, but what we try to do here is to analyze the current. So let's say we do have positive current voltage across the load, and then the current is always positive, and it is like a trapezoidal waveform. And then what you can do is that based on this circuit, you can draw the input current. So when S1 and S4 is on, again you have the case like this. And then during this time, what you see is that I1 equals to I2. And then what you see is that the I1 would be exactly same as I2. And then after a little while, S1 and S4 will switch it off, and S2 and S3 will turn down. And then again, we can draw this current path. And pay attention to the arrows I just drawn here. So you would see I1 would have opposite direction as I2. So since I2 is positive, but here I1 is opposite direction of I2, then your I1 would be negative during this time. So this sequence could be repeated if you do have repetitive control signals. Then what you see is waveform like this. Okay. And then again we can write down a switching function of this circuit. And in this case, what we can write down is that I1 equals to I2 multiplied by S1 minus S3. Okay, so this is a little bit different from the voltage equation. In this case, I1 equals to I2 multiplied by the switching function, but in the voltage, is voltage V2 equals to V1 multiplied by the switching function. And from the observation of the current, you would see this equation actually is 100% correct. Then next case is from DC to AC, which is what we usually call as inverter. And then let's say you have a DC voltage, so that's a constant value like this. And then again you would switch S1 and S4 together, and then what you see is a loop like this. Then the positive VDC is added upon the load. So that's the reason when you look at VAC, is a positive waveform during this time period. And then what happens is that S1 and 4 are turned off, but S3 and 2 are turned down. And then what you see is this: the positive of the DC voltage is connected to the bottom of the load, and then the negative of the DC voltage is connected to the positive, to the up portion of the load, which means this time what the load sees is the negative of your input DC voltage. So that's the reason you have this negative waveform here. Okay, so again, by rotating the sequence, you would generate continuous AC waveform. So this is the generic DC to AC inverter. And again, we can write down the switching function, which is VAC equals to VDC multiplied by S1 minus S3. That's one very important thing you need to notice on this slide, is that S1 should never equals to S2. The reason is that if you have S1 equals to S2, then you would have a short circuit, the DC source would be shorted by these two switches. Same thing for S3 and S4. They shouldn't equal to each other. And again, this is for the safety of the circuit. So in the DC to AC, this phase lag should never be each phase lag should the switches in each phase lag should never be turned on at the same time. Okay, so that was the DC to AC very generic circuit. Then let's look at the generic circuit for the AC to AC. And then what do you see? This is exactly the same circuit of the rectifier, the first generic circuit we showed. And you may ask, is this a mistake? But actually it is not. What we see is that the same circuit but different control. So let's say we turn on S1 and S4 for a short period of time like this. And then from the analysis of the rectifier, we would know during this time V2 equals to V1 multiplied by S1 minus S2. And also, because S2 equals to S3, so this to be consistent with the earlier slide I wrote, it's equals to S1 minus S3. And then at this time, S1 is 1 and S3 is 0, so you have 1 multiplied by V1, so you have a positive voltage here. And then when the input voltage is negative, you turn on S2 and S3. And then still based on the same equation. This equation is true no matter at what time duration. And then what you see is that S1 minus S3 would be equals to minus 1. The minus 1 multiplied by a minus voltage, which is this part, you would get a positive voltage output here. And then you do another switch, you got positive, another again positive, and then positive. And then when you look at this sequence, you would see the passes, actually the lengths are increasing, so, and it is follow a certain pattern. So these switches are not turned on at the random time. The way we turn them on is basically to give you a fundamental waveform. So basically, if you do the Fourier analysis of this sequence, you would find a fundamental component like this, and this would be continued into the negative half cycle. And then this is a waveform that has a frequency different from your input voltage, and also the amplitude is different from your input voltage. And then basically we realized AC to AC conversion, and the frequency is changed and the amplitude is changed at the same time. So this is the generic circuit for the AC to AC conversion. So far we covered generic circuits of AC to DC, DC to AC, and AC to AC. We will not talk about the DC-DC converter. That is our first topic in chapter 2, and at that time you would see the influence of the passive components on the output of the converter. So we will cover it, but just not this time. And then the last topic of the first session of the seminar, the power electronics in hybrid electric vehicles. And it is estimated that the power electronic circuits right now represents 20% of the material cost, additional material cost in the hybrid electric vehicles. And it is not as expensive as the battery, but together with electric machines, they are as almost as the cost is almost the same as the battery. And the goal, future goal for the power electronics is to reduce the size and the cost to 1/3 of what it is now in the vehicles. So just an overview. Let's say you do have a Toyota Prius or Toyota Camry. So what's inside? You have a high voltage battery pack. This voltage, depending on which vehicle you are talking about, could be from 200 watt all the way to 350 watt, depending on the vehicles. And then on the drivetrain, this DC voltage is fed into a boost converter. So at the output of this boost converter, you would have another DC voltage level, but the amplitude is higher. And then this DC is fed into 2 inverters. Each inverter drives an electric machine. So this is basically a planetary gear here, the transaxle, and then 2 machines, 1 generator, 1 motor. And the engine is also connected to the same place, and the planetary gear. But when we look at the power electronics, basically this block here, 2 inverters and 1 boost converter. As I introduced earlier, in Toyota Camry, the motor inverter is 105 kilowatt, and the generator inverter is 75 kilowatt. And so this is power electronics in the drivetrain. And then the air conditioner in the hybrid electrical vehicles right now or electrical based. The reason is that now if you use electrical machine to drive the air conditioner, the efficiency is higher. So we directly get the high voltage out from the battery and drive the air conditioner. And in the air conditioner, what do we have is an induction machine plus DC to AC inverter, and this is to drive an induction machine. And then in the vehicle you do have 12 volt battery. In the old days you would have an alternator to charge the battery, but with hybrid vehicle you do not do the alternator anymore. What you have is a DC to DC converter. It changes the voltage from 200 to 350 watts, again depending on the vehicle, to 12 volt. Okay, and then for different users, they may have different requirements on the AC output from the high voltage battery. Here we are talking about 120 volt AC, and it's at 60 Hz. So game fans can plug in the PlayStation. Contractors, they can plug in the power tools. And this is our auxiliary power supply from the high voltage battery. And this again is a DC to AC inverter. And both the 12 volt DC-DC converter and the auxiliary power supply, they have multiple stages in it. Means they have first the DC to AC, then high voltage and the high frequency transformer, and then after that they change the high frequency AC waveform to DC again, and then in the case of auxiliary power supply it goes back to AC. So it's quite complex. The reason we want to do that is mainly for safety issues, because if you do not have a transformer in between, then you are connecting the high voltage ground to your home appliance or to the 12 volt system, which is not very safe. So those circuits have multiple stages with a transformer inside. So this actually is an overview of what are the power electronic circuits in a full hybrid. Why I say full hybrid? Because hybrid vehicles actually can be categorized in 3 different types, which I will cover in a couple slides later. But let's answer one question first. why we need to do hybrid electric vehicles in America. Why it is important? I think everybody now knows it, because we have this energy crisis, and also we have the pollution and global warming. And recently, that's one more reason, because Toyota Prius is unstoppable. And actually, it is indeed literature unstoppable, because if on one hand, if you look at the sales data, in last month, in February 2010, compared to the same month in 2009, the sales actually increased 10.2%. And in this year already, in North America alone, in US alone, it says the Toyota Prius has been, the sales is already over 16,000 vehicles, and it has a 7.2 increase. Another thing I want to point out in this slide is that on the left-hand side we have the historical sales data for the for hybrid vehicles, and we see a peak at 2007, and then it drops very quickly. And the reason is actually, if you look at the oil price in this picture here, you would see the oil price drops almost at the same time. This is around 2007. So means our purchase habit actually is indeed related with the oil price right now, which is still not a good thing, but hopefully in the long run more people would start to buy hybrid vehicles regardless the price change of the oil. And then let's talk about the categories of the hybrid vehicles. We usually have the micro hybrid, which means we only have a small DC voltage bus in the vehicle, and then the electric machines used in the vehicle has very low power rating, 4 to 8 kilowatt, and usually it is only used as integrated starter and generator, so it's start and stop. And you can only save 5 to 10% of you can only do the 5 to 10% efficiency improvement for the whole vehicle. And then there's mild hybrid. Sometimes people also say that it's a medium hybrid. It has a higher DC bus, so indeed you would have a nickel metal hydride battery or lithium ion battery inside the vehicle, give you 120 watt to 200 watt. And then you have electric machine rated from 10 kilowatt to 20 kilowatt, and then this actually could function as a motor to crank the engine up, to accelerate, to help the acceleration a little bit, and also it still has the start and the stop and stop function, so integrated start and generator function, and the energy saving is 20 to 30%. And my favorite is a full hybrid. Basically, it has a very large high voltage battery. Voltage in extreme case go down to 170. Actually, that's at very low temperature too. And then can go to 400 watt based on current vehicles. And then the key technology is that inside you do have high power electric machines. Let's say the two modes, the GM2 mode, you have two 50 kilowatt electric machines in Chevy Tahoe. So that's actually similar for full hybrids. You have high power electric machines. Then as a result, you need high power, high voltage power electronic circuits to drive those machines. And the energy saving is 30 to 50%. So that's really good energy saving. That's reason now full hybrids actually has better sale than micro and a mild or medium hybrid. And then this table is just a summary of different power electronics units in the different categories of hybrid vehicles. And a couple of things I want to point out: the voltage and the power ratings basically are similar to what we had in the last slide. And then that's one column I haven't mentioned is the switching method. It says hard switching and soft switching. Basically, this is the soft switching is a way to reduce the transient loss of the switching. Basically, every time you turn on or turn off the switch, during that transient, you would have some energy loss. And then by implementing some control techniques with additional passive components or sometimes even active components, you can reduce this energy loss during this switching transient. So that is a technique called soft switching. In this class, in this seminar, we will not cover soft switching, but I want to know basically for switching itself, there are two categories: hard and soft switch, hard switching and soft switching. Okay, so also for different power rating and also different sizing requirement, you would see the converters and inverters sometimes are liquid cooled or sometimes are forced out cooled. Really depending on where it is located, how much is the power rating, what is the ambient temperature. For example, this guy is 55 degrees C, but if it is under the hood, you need to see 105 degrees C. And then at the end of the seminar, I want to give you some useful websites that you can look at later on. The first two is related with Power Electronics Society. The second link is very useful. It has some Java-based GUIs, basically some very interesting animations that you can control to show how the converters are operating, and also some basic control techniques. Different PWM strategy is also showed in this website. And then if you are interested in the manufacturer side, especially power supply side, there's a website for Power Electronics Manufacturer Association. This is mainly a lot of the participants are manufacturers in the United States. And for switching devices, this is mainly for switching devices. The most popular websites are IR. Usually you can find good MOSFETs. Small power, not very high voltage. Power is limited. And same thing for XYS is MOSFET, and these two are US manufacturers. And the power racks, that's actually Mitsubishi, that's Japanese guys. And the power rating and the current rating is pretty high. The switches you can find in this website are pretty similar to the ones used in hybrid vehicles in the traction drives. So this is from Japan. And then Infineon and Semicron, they are from Germany. And what you see is that both of them have very good technology of IGBTs, the high power and high current devices. So it is a little bit frustrating actually in United States. When you look around, you cannot find domestic manufacturers who can provide silicon chips and switching devices that are suitable for the traction drives of the hybrid vehicles, which is the most important part in the hybrid technology. I think actually IR and XYS, they do have components in medium and mild hybrids, but since most of the products are MOSFETs and the voltage rating and the current rating is not high enough, so it is on the manufacturing side still United States actually before it's leading, but now it's lagging and it's not a good situation. And later on, when I start to talk about the passive devices, you would see the similar situation. So if you are power electronics guys in company, say we are talking about the Japanese guys and German guys from Germany, do not blame them. Basically, that's because they cannot find anybody here. That's something we need to change. Okay, so at the end, what I want to give to you is a quiz. Okay, so basically, in several slides earlier, I showed you the generic circuits of the power electronics circuits. Okay, and then here I gave you a circuit a little bit complex, two DC to AC converter. To DC to AC in order, connected in cascade to generate this kind of waveform. So this is your VAC. This waveform is your VAC versus time. And then what I want you to do is to write down the switching functions of this circuit. So here in this each place, what you would write down is 0 or 1. Okay, so you would fill in all these blanks, and then by filling correct numbers here, you would get this waveform. One thing I want to point out is that in this waveform, you see during time period TA, you are utilizing the voltage from C2. Okay, and then during time period TB, you are utilizing the voltage from C1. So that actually also decides which switch you want to move to assign as 1, which assign as 0. So please be careful. And then pretty much that's our first session, and I hope you enjoyed it. And at the beginning of the next session, I would give you the answer for this quiz. Thank you.